everyone, and welcome to the Digital Medicine Society's first webinar of the year. I am Rachel Chassie, DiMe's Director of Innovation, and I am thrilled to open today's session. Today we're talking about machine learning, predictive glucose levels, and the future of proactive diabetes management. A quick housekeeping mention before we get started. Today's webinar is being recorded, and the recording and the slides will be available after the session. So no need to feverishly write down notes today. You'll get the whole access later on. And so we do have quite an exciting webinar today. We have with us Amir Hayari, CEO of Bioconscious Tech and founder of Diabits, Dan Goldner, VP of Data Science Operations at OneDrop, Mark Clemens, Associate Professor at the University of Missouri, Kansas City, and moderating for us today is Jerry Fisher, endocrinologist and founder of MD Request. We've put together a fantastic webinar for today. I know we say that every time, but I think today is also particularly fantastic. We'll be discussing how data is used differently in the care for type 1 and type 2 diabetes patients using mobile technologies. And then we'll move on to discuss how big data is made meaningful when caring for patients in the clinic. And as with all DiMe webinars, we'll have a Q&A session at the end. Everyone online is encouraged to submit their questions using the Q&A function you see on your screen. And if you run out of time before getting to your question, do please feel completely free to reach out to us on Slack. Okay, and with that, I'll hand it over to Jerry to get us started. Jerry?
Well, listen, thank you, Rachel. And again, thank you to Rachel and the rest of the team at DIME for getting this off the ground. I'd like to welcome everybody and Happy New Year. As a retired endocrinologist, I've tried to keep my mind nimble by keeping up in the world of AI. I've been aware over the past decade about the enormous data we've accumulated of glucose levels. And I've been waiting for a long time for this to become a useful mechanism as opposed to a Rorschach diagram. And I think we're at that point now, that tipping point. I'm going to sit back right now and listen to our three speakers. I'd like to just put in a little quote here from a statistician named George E.P. Box. All models are wrong, but some are useful. I think we'll find that we have different approaches with the use of data from the three speakers. I think we can all learn from the different approaches and the different ways to manage diabetes that I think will be extremely helpful in the future. And without getting any further interruptions, Amir, go ahead and start.
Thank you, Jerry. Hello, everyone. I'm Amir, the founder of Bioconscious Technologies. We're a health analytics company, and we use machine learning to predict disease complications for patients with chronic conditions. The most pressing need that we target, we believe, is in diabetes for people who require glucose management, as Jerry said, especially in type 1 diabetes for people who need it the most, actually, with the highest level of accuracy. So what we've developed, if you can move on to the next slide, is an app called Diabits. It's an app for patients with diabetes that uses historical sensor data to predict what is going to happen to the patient 60 minutes ahead of time. And these calculations are done every 5 minutes. So at every moment in time, from 5 minutes to the next, these values are recalculated and shown again to the user. For those who are not familiar with the usefulness and the merits of actually predicting blood glucose, this is what blood glucose, on the next slide, this is what glucose looks like if it's continuously recorded for a patient with type 1 throughout the day. And this is a continuous glucose monitoring recording. What happens here is because the body has lost the innate ability to control blood glucose throughout the day, every time the user has a crash or they have excess amounts of glucose, they have to regulate it themselves. And obviously, if there's too much of it, excess amounts of sugar crystallizes in the blood, and you're putting your eyesight at risk, you're putting your soft tissue at risk. And the other main issue is, if you look at the bottom left side, is the risk of death. If there is not enough glucose in the blood, especially for a type 1, in a matter of hours, you can go into shock, coma, death. And for a patient with type 1 diabetes, what we try to help them with are those instances. We want to bring their glucose closer to the healthy glucose range, and we want to make sure they actually avoid that red dot on the graph. So I've put together a few examples in terms of what will happen if we actually show patients their future glucose values 60 minutes ahead of time. if you look at on the next slide, because of the risk associated with having very little blood glucose and having tight control that will result in hypoglycemia, most often than not, the patient would prefer, especially, on this slide, you're looking at the patient that had a near-death experience where they passed out, they were concussed on the floor for 2.5 hours until somebody found them and they took them to the hospital. As a result of that, they actually prefer hovering high, and those flat tops are instances where the blood glucose is so high, the continuous glucose monitor is not actually recording it. It's waiting for the value to come down to report it to the user. And obviously, 30 days after we show them their glucose values, you can see the dramatic difference on this slide in terms of what happened day 1 when they actually looked at it for the very first day, and then day 31 once they actually got a hold, got a hang of, if you will, of their blood glucose or fluctuations, and they got into a routine of using their blood glucose. Same thing on the next slide, if you notice, day 1, and what it does is usually when patients are trying to maintain a tighter control, you have instances of hypoglycemia, which are equally dangerous. So we will try to help the patient avoid those instances. And there are not a whole lot of surprises there. You tell someone, it's kind of like a GPS. You tell someone there's traffic one way, they're gonna take a different route so they can avoid the traffic. Especially if you're pressed in time, you tend to trust your GPS. And this is the same thing. Going from day 1 to day 31, you'll see dramatic differences where now the patient sees how the glucose is behaving and how they can better actually maintain it. And obviously there are some other cases where for people who have better control, if you look at on the next slide, it takes some time for people to actually get a hang of how to use their predictions and how to go from a type of management that is very retroactive to a type of management that is proactive. But most often than not, what we see across the user base that we have is having the ability to see your glucose fluctuations ahead of time will give you a foresight into how you can better manage your glucose. Now, we use machine learning to basically train our models, use a variety of them. And so I kind of wanted to start off by talking about machine learning and how we can potentially use it for predicting blood glucose accurately ahead of time. The answer to that question is, what is machine learning and how do we use it? I'm really not sure. It is one of the hottest fields. I'm sure you guys are no stranger to it. It's one of the hottest fields around, and there's very little consensus amongst machine learning experts into what truly is actually a dynamic algorithm that learns and understands and so on and so forth, and what is human-assisted learning or supervised learning and so on and so forth. So the way I kind of rationalize it for myself is if you think of machine learning like the Lego company, there are 3 sets that we can all agree on. There's the supervising methods, where supervised learning, but they're nothing new. They've been around since Alan Turing, if you will. And so they've developed over the years and they got slightly more complicated. And then we have unsupervised machine learning. One of the most popular methods when it comes to unsupervised machine learning is the neural nets. Usually comes into effect when you have tons and tons of data that you want to analyze, and it's almost impossible for a human to go through them and find patterns. And then there's also reinforced learning. What we do is we focus most of our attempts on supervised learning, because when we got started, we had patients that will come on board and start using the app, and we had to generate a library for them. So we didn't have tons and tons and tons of data. So unsupervised learning was one of the things that was basically out of the question for us because we didn't have enough data to train the algorithm. So we focus our attempts on supervised learning more than anything else. But we also bring in elements of reinforced learning into the equation, so that when the algorithm misses instances where it tries to predict, but it misses by more than a certain percentage of the actual value, it's able to figure out what has happened using a user-generated library and try to add those to its prediction and training library, if you will. So the way we look at glucose metabolism, we see a system with multiple parameters. Regardless of diabetes, glucose metabolism is different from individual based on our data from person to person. It's sort of like a composite of your habits, behaviors. We can go to the next slide on this one. There we go. Thank you. dependent on your state. It's dependent on the food, the habits. We have some preliminary data that, can show correlations between even the weather. If the weather outside is sunny, most often than not, the temperature is good. Most often than not, people tend to have a tighter glucose control. If it's cold and snowy like it is today in Vancouver, people tend to hover higher than usual by about 20%. So there's a lot of data points that you can gather and you can make predictions on. So the way we start about the whole process is, first of all, is data collection. So on the next slide, if you can show, that would be great. Thank you. So we pull in multiple data points that are available to us. We get glucose data that's coming in continuously. We also get sensor data. So there's exercise, which is reported either by the phone if you have the phone on you, or the new watches come with an accelerometer built in, so they can give you a lot of statistics around how much the patient has moved, how much activity they're having. A lot of them come with heart rate sensors. Most often than not, the data is somewhat useful for the newer generation ones. And obviously on the app itself, we allow people to either integrate, manually put in their insulin information, or connect it to their insulin pens, or if they're using Night Scout, all that information pulls in. And we also allow them to put in meal options, what they've had and what they think they've sort of had. And what we end up with on the other side is we end up with a massive library, which is basically our population data. And we end up with smaller user libraries that are specifically on one user's data. What we do is we start by training a support vector machine on CGM data only. We have another model that's a decision tree paired with a support vector machine. We sort of train that one on any parameters that come in. So if there's CGM data, if there's exercise data, carbs, insulin, heart rate, all that data goes into training it. And then we also have we use the population data to train a neural net model, because everybody's favorite is a neural net model, and they obviously want to outcompete one another. But basically, we have now 3 different models that at any moment in time are making a prediction of what's going to happen 60 minutes ahead of time for the user. And what we do is we basically collect their predictions. And what we look at is, first of all, we want all these models to outperform our baseline for predictions. And what our baseline basically is a straight line that says if you start with, let's say, 170 milligrams per deciliter at the top of the hour, you're going to end the hour around the same value. And interestingly enough, in our case, based on our data, what we found out is for type 1 diabetic, if you say nothing has happened and you're going to end up with the same value at the end of the hour, you can basically, based on error grid analysis, you can be right more than 70% of the time. So the baseline, and the computer figures this out pretty quickly. So what you want to do is you want to actually force the models to prefer, rather than a straight line, prefer predicting curves. So what we want to, the way we design it is we want to make sure that, first of all of these models outperform a straight line. And if at any moment in time, any of them perform less in terms of accuracy than a straight line, they actually get penalized and they go back to retraining. But then from the 3 models, what we look at the most accurate one, and the one that actually did a really, really good job the past hour in terms of predicting future values, will get the luxury of predicting the next hour in terms of what the actual value should be, and it goes from there. And so most often than not, what we see is for patients who have a wearable device and do a good job of keeping track of coming back to the app on a daily basis, we see that the hybrid model, decision tree plus the support vector machine, outcompetes both the CGM only, the support vector machine, as well as the neural net that is based on population data. That's something interesting that we can talk about later down the road. But what I want to sort of talk about is how we define and measure accuracy. Now, there are many, many ways that we can measure accuracy when it comes to making predictions. But what we focus on is error grid analysis. So there are many different types of error grid analysis out there. But what we want to make sure is that when we make a prediction, we're actually doing a good job of predicting the actual values. So what we want is that dotted line of one-on-one correlation. So the value that was predicted ends up being the same value an hour later. And most often than not, what ends up happening is that, you know, about roughly 10%, less than 10% actually, of our predictions are not in that one-on-one correlation, which is really, really good for us. We've now basically increased our accuracy since, you know, last couple of years. And we've modified our error grid analysis. And what we are focusing on right now is trying to get almost all of them for that horizon into that one-on-one correlation. But often than not, what ends up happening is that you end up missing that value. It's not that big of a deal if you miss the value. It's important where you're missing. And so what we want to do, because of the high risk associated with managing type 1, we want to make sure that, you know, we don't miss in areas where we're misidentifying, you know, instances of hyperglycemia. We are not predicting that something's not going to happen when it is, and we are not, you know, basically we are interfering with treatment, but we are not misinforming the user. So what we've done in the past is basically we've publicized some different types of error grid analysis. We're gravitating more towards, right now, more towards PARC on the next slide. And what we want to focus on, we want, as mentioned, it's the same process. We want to make sure that the predicted values and the actual values have a one-on-one correlation. So they actually end up being on the dotted line or around there. But often than not, as you can see, you'll have points that end up in different regions. And it could be for a variety of reasons. This could be because the model predicted that the user will have a hypoglycemic episode in the next 60 minutes. The user realized it. They took corrective actions, and they ended up completely avoiding that instance. That didn't mean the model was wrong. That actually means that the model did what it was supposed to, but the actual value will end up farther away from the real value. So what we want to do is we want to make sure when these instances happen that the computer is not, the algorithm is not being penalized or overtrained. At the same time, want to make sure that we have enough data and statistics around instances where there are these discrepancies between predicted and actual value. So on the next slide, what we have is when we actually do a prediction, we look and see if the actual value is within roughly 10% of the recorded value an hour later. If it is within 10%, we give ourselves a pat on the back and we go home. If it's not, however, we ask the users to use the journaling mechanism on the app and tag the readings. And what that allows us to do is to now create a user-classified library of blood glucose data in presence of different factors such as corrections, insulin, activity, and so on and so forth, and add that into the training library that we have. So the next time this instance comes up, the model is performing better. And I've included a screenshot of what the tags basically are. You can basically pick and choose any of these. The amount of insulin, you can change your insulin to carbs ratio, you can basically put in anything, and all that information will be used to retrain the algorithm when that happens. And right now, the best frequency that we've discovered so far for retraining is every 2 weeks. So once the algorithms are trained within the first 7 days that the user accumulates enough data points, then they go back to retraining every 2 weeks to make sure that they're staying up to date. If the user picks up new habits or if anything changes like the season, they're able to pick that up and reflect it in their predictions. With that said, I'm gonna pass you know, it along back to Jerry, see if there are comments or questions, and then we can carry on with the rest of the webinar.
Well, thank you, Amir, for a very succinct description of a very complex process. And just like in my grandson's Sesame Street lessons, what's the same and what's different, Dan's going to present the one-drops approach. And just to give you guys a timeline, remember, diabetes was first diagnosed in 1500 BCE. The word mellitus was added in 1700s, and it was involved with sweet urine. Fortunately, we don't have to taste urine anymore because we started with blood testing in 45, dextro sticks in 1965, and now the world of CGM has opened things up. So Dan, if you'll take the baton and tell us about one-drops approach.
Sure, thanks. So Amir was talking a lot about making predictions for, for people who are wearing continuous glucose monitors and using the data from those continuous glucose monitors. And that's a very, very important thing to do. As he pointed out, if you are wearing one of those monitors, it's probably because it's very, very important that you take action moment to moment through the day to manage your blood glucose. CGMs, continuous glucose monitors, have been reimbursed largely for people with type 1. They're starting to be a little more for people with type 2, especially advanced type 2. And that is changing, and the use of CGM is increasing. However, it is still the case, and it's going to be for a long time, that for every person who is wearing a continuous glucose monitor, there are hundreds and hundreds of people without diabetes who are not. Most people are checking their blood glucose a few times a day, actually most often only once a day, using a finger prick and a meter. And so today I'd like to talk about how OneDrop is using blood glucose prediction to support people with type 2 who are not on continuous glucose monitors. Especially when we're talking about type 2, diabetes can't be solved from the doctor's office. Now, a couple of caveats about that statement. The first is the work that is done in the doctor's office is critical and important. And you can't solve diabetes without that. And the second caveat is that as soon as I'm done with my slides, Dr. Clements is going to educate me about all the ways that you can solve diabetes from the doctor's office, even reaching out to patients in their home environment. But that's not the norm. The norm is that people spend maybe an hour a year with their doctor, maybe it's 2, and the rest of the time they're at home on their own trying to figure out how their eating and their exercise and their medications and their mood and the weather and everything else is affecting their condition. Doctors don't have the time to monitor, mentor, motivate, and educate people in and out through the daily decisions about living with diabetes. And that is the situation that OneDrop was really created to solve. So what OneDrop is it's virtual integrated care. And I'm going to spend just this slide telling you about the program in general, and then the rest of the slides telling you about our predictive algorithm and how it's used. So if you're part of OneDrop, you have your very own certified diabetes educator that you can text anytime. It's a real person, not a chat bot, and it's a person who knows you and who can answer your questions as they come up in your life with diabetes. We make a blood glucose meter that I think is gorgeous. And actually, when I first started working at OneDrop, I was surprised at how much that mattered. But turns out people don't like carrying around equipment that looks like garage door openers. They like carrying around equipment that makes them feel good about themselves, and where receiving it feels a lot like shopping for something nice. So there's that. We have a strip subscription plan that is one of the most affordable on the market. A lot of people find that getting strips by subscription is cheaper, through us, is cheaper than their copay and more accessible. And we integrate with everything we can integrate with. So with your Apple phone, with your Google, with Fitbit, with Alexa, with Siri, you can talk to OneDrop from your Dot at home or your Echo. And the idea there is just to make sure that whatever people want to use, if they're using Lose It to manage their nutrition, if they're using any kind of app to help kind of get all the information organized in their life, that we're going to be able to work with them instead of making them learn something new. So the part that I'm here to focus on, though, is the automated decision support, which is based on blood glucose prediction. And so that's what I'm going to talk about next. So as Amir was saying, diabetes is a data disease. There's glucose levels, carbohydrate counts, insulin dosages, the effect of exercise, and being able to track how all those things combine to affect your individual body. And I have the great privilege every day of turning those data into better health outcomes and better lives for OneDrop users. As you can see from the slide here, we have a lot of data, and the sheer volume of experience reported by OneDrop users means that we can give predictive insights to users who are in new situations, because other people maybe have been in similar situations. We can give new information, or we can give predictive insights to users who don't log a lot of information. And we can even give insights to new users right away as soon as they start with the app, because the model that we use is not looking just at your personal history when it's doing a forecast for you. It's also looking at the information from the entire population, and that population grows larger every day. So on the next slide, I'm going to look at some examples of how it works, and I'm going to describe how it works under the hood a little bit, and then I'll tell you a little bit more about what it's like for the experience for actual users. So if you're using the OneDrop app and and your phone or your watch picks up that you've been moving around, or maybe you deliberately enter a meal, or you take a blood glucose reading on our meter or another meter, and it automatically gets Bluetooth right into the app. As soon as there's new information there, there's Rach, we're going a little faster. Can we back up to that couple of slides? One more. Perfect, right there. Okay, so so as soon as that first blood glucose information hits the app, the machine generates a forecast. And for for people with type 2, the blood glucose values are a lot less volatile than they are for type 1. And so what that means is we're actually able to get good predictive capability out for 8 hours for this population. So a prediction is made of what the blood glucose is going to do over the next 8 hours. Okay, cool. Next slide, please, Rachel. Thank you. A little while later, if that user logs a meal, that's new information, and so the system automatically updates to take advantage of that information and produce a new forecast. All right, next one. And I want to go through the process. It's actually very similar to what Amir was talking about in terms of how we train and test the models. Here we've got an example where through the day, 9:30, 12:30, into the afternoon, the green lines represent times when this user logged a meal, and the orange lines represent times when this user either logged or their devices picked up activity. And then it gets to be 30 minutes past midnight, and it's time for bed, and the user takes a blood glucose reading, and it's up between 220 and 240, and so the system generates a forecast. Now, this is a historical example. We have this data over years. We have 200 million VGs, and so what we can do is actually look back and say, well, what was the next time this user actually took a VG, and what was it? And so if we do one more slide, we should see it there, and it's not there. The next thing that happened, it looks like it's just off the slide, so you're not seeing it on your screen, but at 9:30 in the morning, the user took a VG, and it was a little above 180. So this particular forecast, which was about 7% off the actual value. So by looking back over the history and running these retrospective forecasts, we can measure what the accuracy of the algorithm really is, and that's what I'll tell you about on the next slide. So for 1 to 12 hour forecasts for people with type 2 diabetes who are doing self-monitoring, so finger prick check, 86% of our readings are within 50 milligrams per deciliter. Now, if you're familiar with diabetes, that is not fantastic accuracy, but it's in the ballpark. And the point is that most of our readings are in the ballpark. If people tend to be, in the hundreds or 200s or 300s, this tells you which zone you're in. More importantly, 75% of the time, those readings are within 34 milligrams per deciliter. And for a lot of readings, that is within that same range that Amir was talking about, trying to get in before. 50% of the time, we're within 16, which is getting to be very accurate, and about a quarter of the time, we're basically right on at 7. Now, remember, many of these users are not using insulin. They don't have the same kinds of extreme highs and lows, especially not the lows that you see in people with type 1. And so this accuracy is sort of for a different purpose than managing the next hour. And so what that purpose is what I'm going to talk about next. So what will happen is, as soon as you enter new information in the app, a forecast is calculated, and you get this message saying, hey, your blood glucose is going up, but not too high in the next 4 hours, or it's going down, but not too low in the next 3, or it's going up higher than it should be over the next 6, whatever it is. And along with that is a message that's either educational or motivational, and that is selected based on your history and based on what the forecast is that you're getting right now, so that message is as relevant as it can be. And this is really the most important part, from my point of view, of the entire program, which is that if with people with type 2 who might be measuring their blood sugar once a day, often that once a day test is sort of a pop quiz that they don't know how to study for. Unless they've had really good access to education, either through their doctor or certified diabetes educator, it's very hard to know what's going on with blood glucose and what causes it. So what happens in this system now is I've gone through my day, I've entered that something happened, and boom, there's a forecast saying what's going to happen in my body as a result of what I just did. And that we feel is a much more salient moment for people to start paying attention to how their body works than looking back at the end of the day and trying to remember what happened that led to this cumulative result. And as we can see from the stats on the slide, people really like this. 80% of our users over the time that we've had this launched have given feedback, and 93% of that feedback has been in the "this is helpful" category. So this is one way that people get access to the forecast. The next way is on the next slide, which is that you can also get a forecast. You can go to a place in the app and get your forecast anytime you want, so on demand, making your glucose forecast as available as a weather forecast. And when you look at that graph, you get some further information. The pink zone in the back of the graph is actually a customized target zone. You saw on Amir's slide that there was sort of a target rectangle we're trying to keep people in. And we recognize, though, that when you eat, your blood glucose is naturally going to go up for a little bit, and that's okay. You can in the literature, we find that people with healthy long-term average glucose do have glucose that rises a little bit after meal. That's natural. And so the target zone there is automatically adjusted based on when you ate or when your typical meal times are. And you also see around that graph some tiny little dots, a little railroad track on either side. And that railroad track will either get wider or narrower depending on when the forecast is when we're more confident about it or when we're less confident about it. So you get a sense of how much the model really is sure about what's going to happen. Great, let's go to the next slide. Yeah, that's about it. Our aim is to bring predictive support for self-care to everybody on the planet with diabetes and a smartphone. And it's been really gratifying to be able to make this cutting edge technology available to people all over the world.
All right, well,
I'll send it back to you. Yep.
All right, Dan, that was excellent. And again, I want to point out the different populations that both Amir and Dan are dealing with in a sense. The use of CGM, the other side where you don't have CGM. And how they're both important, particularly in the area of teachable moments. Now to finish up our speakers, there's someone who I am very jealous of because I've worked with Mark on the Gluco board, and I'm impressed with the fact that he's not only an excellent clinician, but he's also an excellent scientist, very aware of things of the other side of the computer and the hardware. So he knows hardware and software. So I'm sure you'll be fascinated with the slides I've already looked at. Go ahead, Mark, and tell us what's going on from your side.
Yeah, thanks, Jerry. So this is Mark Clements. We can advance to the next slide. For those of you who don't know me, I wear several hats. So I am at Children's Mercy Kansas City in the center of the country. And in May of this year, I became the Chief Medical Officer for Gluco. And then I have several grants and other consulting arrangements. Today, I'm going to talk to you about a project that we have been running at Children's Mercy Kansas City with support from the Helmsley Charitable Trust to apply predictive analytics to patient selection for modified pathways of treatment in the clinic. And I really have to pause and thank Dan and Amir for their talks because I think, number one, they helped define a lot of things that they will save me from having to define. And number two, I think that what they're both doing is showing us interventional pathways that are unique and different and can tailor care to the individual needs of persons with diabetes. And so what we're trying to do to marry this all together is to identify the best candidates for those interventions and other interventions like them. You can advance to the next slide. So I'll just talk briefly about why I consider machine learning in the clinic. I'll talk a little bit about a model we have to predict rising A1C, a model we have to predict hospitalization for diabetic ketoacidosis. These are both for our pediatric type 1 diabetes populations at Children's Mercy, where we care for about 2,150 youth with type 1 diabetes. Finally, I'll talk about marrying those predictions to implementation science. Next slide. So, you can advance until you see 4 pictures at the bottom. You know, I like this quote from Henry Nix, that data does not equal information, information does not equal knowledge, and most importantly, knowledge does not equal wisdom, because that speaks to my experience as a clinician in modern healthcare today. We are surrounded by oceans of data, we have rivers of information and small puddles of knowledge, and occasionally we have the odd drop of wisdom. And that was not a specific plug for one drop, but it seems to fit. All right, next slide. So why consider machine learning in clinical care? Next slide. So if one looks across the data from the US Type 1 Diabetes Exchange, which was a network of 84 centers that from 2010 to 2019 conducted health outcomes research together, and which I had the good fortune to chair from 2016 to 2019, you can see that we have a problem. If the target hemoglobin A1C is 7% or below at the bottom of the y-axis for adults, and the target for youth is 7.5% or below, although it's gotten a little more nuanced with the new ADA guidelines this year, you can see that according to these median numbers by age, very few people are actually making their targets. And in fact, you can see that if you look across childhood, most of the lifetime risk of complications from type 1 diabetes are accumulated because you have a significant deterioration from about age 8 to about age 18 in glycemic control. And then it takes until about 30 to settle into what I would call an adult pattern, although that's also still not in control. And so I call this curve on the left-hand side Mount Kilimanjaro in my clinical practice. This is the mountain we're trying to climb, and the mountain that we're trying to flatten. Next slide. Another important bit of information for you is that when you look at Mount Kilimanjaro, it is not the case that every young person with type 1 diabetes will have a significant rise in their hemoglobin A1C. And these data from our colleagues at the DPV network in Germany show this quite nicely. So they performed latent class analysis to look at trajectories of hemoglobin A1C across childhood. And they found, using this approach, that they could tease out 5 unique trajectories of hemoglobin A1C. And as you can see, there are youth who have stable patterns across childhood in the red, black, and green, but in the blue and the gold, you can see that about 18% of youth will experience deterioration across their time as young people. Next slide. So we have leveraged the fact that this can be done, and that about 18% to 22% of youth, depending on the population you look at, will have deterioration. And we have worked with our data science partners at SIFT in Boston and have developed a machine learning model using a random forest approach that looks to predict the rise in hemoglobin A1C for youth who will experience a rise between now and the next clinic visit 70 to 110 days from now, which covers the most common interval between clinic visits in our clinic. And as you can see in the gold bar at the top, we can get a precision just using electronic health record data. So this includes all of the discrete data from our clinic, from ER visits and urgent care visits, and any other clinic with which the children have an encounter at Children's Mercy. It also includes the free text of all the clinic notes. So we perform feature engineering using natural language processing from those documents. And we can get a precision, between 50 and 60%, depending on the level of rise we're trying to predict on the x-axis there. You can also see that if we perform simple regression based on past A1C or past mean blood glucose, that model performs close to the machine learning model, but that there's significant deterioration as you approach the more extreme rises in hemoglobin A1C, and that's in the green curve. And this compares to a null model where you can just see the background rate at which specific rises in A1C of 0.2, 0.4, 0.6%, et cetera, occur. Next slide. So we also know that the diabetes self-management device data are an incredibly valuable source, not just for predicting glucose in the next hour or the next 8 hours, but also for identifying features that may predict changes in clinical care in the next month or 3 months. So we have incorporated all of these device data into our predictions. Next slide. And you can see how the incorporation of these data enhance the model based on precision. So in this case, what we've done is if I make a prediction at our clinic visit today about what's going to happen at the next clinic visit, I'll get a certain precision to that prediction. But if I now look at your diabetes self-management device data 8 weeks prior to the next visit, or 6 weeks, or 4 weeks, or 2 weeks prior to the next clinic visit, if I continue to revise the model, you can see how after today, we can actually get a higher precision between 60 and 70% for rises in A1C. And the deterioration that you see in these precisions on the right really has to do with the fact that we had a limited cohort. So there were very few people in the cohort that had rises of greater than 0.7%. So we're working on increasing the size of the cohort for the development of these models. Next slide. The next thing I'll talk about is how we're applying machine learning to predicting hospitalization for diabetic ketoacidosis. And one of the things that I think really comes out in this is that machine learning approaches, whether they're supervised or unsupervised, or incorporate feature engineering like NLP, they really are amenable to the dirty, messy, raw, partly reliable data from electronic health records. Next slide. So why did we decide to try to predict hospitalization for diabetic ketoacidosis? These are data from Children's Mercy's own accountable care organization. And I don't want you to pay attention to the specific numbers in terms of dollar values, but I want you to pay attention to the fact that if one looks at non-pharmacy costs for type 1 diabetes, that inpatient stays comprise about 30% of all those costs. And so we think that's an important target for intervention, both to try to reduce cost for the payer systems, and in our case, our accountable care organization is at risk for a certain number of these youth in terms of the payment model, and also obviously to reduce morbidity from DKA and allow us to better steward our hospital beds so that we don't fill, our census doesn't fill, which happens quite a bit at children's hospitals. All right, next slide. So in this case, we've used a recurrent neural network, and I'm not an expert in these techniques, but I'm told as I'm getting educated by our data science partners that essentially what we're doing is we're creating at each time node memory for the previous prediction and incorporating that memory into the new prediction. One of the interesting things we've done in these models, as well as we've taken the predictions for hemoglobin A1C trajectories from our rising A1C model, and we've incorporated those into this. And it turns out that they're very useful in predicting hospitalization for DKA. Next slide. So these are just some preliminary data that we have that we hope to be presenting at the ADA conference. So this is 180-day probability of admission. We started with 180-day probability of admission because we wanted to cast a wide net, and we'll be doing some work to refine that and try to narrow the prediction to a smaller number of days, like 90 days or 60 days. And what you can see is that if one looks at a rank-ordered list of patients by probability of DKA admission, if I look at the top 5 patients by probability of admission on that list, our precision for identifying those individuals is 100%. If one looks at the top 10, it's still 100%. If we look at the top 25 now, we have a significant drop-off of 48%. But this is still existing on a background rate of admission for diabetic ketoacidosis of 6% across members in our clinic. And so what we've really done here is created a cohort that is enriched for risk of hospital admission for DKA. And the point of this and the rising A1C model is that we can now turn our attention to taking these risk-enriched cohorts and selecting individuals off of those rank-ordered lists to send them down different pathways of care. And in using quality improvement methodologies, we can actually perform pre-post testing across these cohorts and determine whether we get a signal for improvement. Because remember, no clinical trials have been done to try to improve these outcomes, because in clinical care, these types of predictions haven't been made. So that may inform the design of clinical trials for interventions that haven't been tested in clinical trials, using a lower cost approach that allows us to get a signal for improvement in clinical deployment. This really works well when you're thinking about behavioral interventions, because in a lot of behavioral interventions, it's not necessary for you to perform a full randomized controlled trial before you start to pilot test it in clinical care. Next slide. So we use the model for improvement in the chronic care model. We use the Deming wheel, plan, do, check, act. And we really just ask ourselves how to make a change that is an improvement. Next slide. And the goal is to create an integrated care delivery system to improve care of individuals with type 1 diabetes and their families, and the fiscal health of the diabetes center. Next slide. So how do we do it? Well, you know, we assembled a group of experts, and we put together a quick hit list of potential interventions and put them through a prioritization matrix. You know, there's not a lot of science to this, except that we reviewed literature, we looked at pre-post studies, and we looked at expert opinion and decided there were some potential quick wins that might be high impact for us. Next slide. So what have we done? We've taken those interventions, we've added them to our key driver diagram to drive the quality improvement effort in clinic. And you can see that there are quite a few interventions, but all of the interventions are matched to key drivers for improving hemoglobin A1C in this case. Next slide. And for our rising A1C model, the interventions we've been testing are data sharing plus directed home telehealth visits every 2 to 3 weeks between now and the next visit. We've started to incorporate an intervention for peer mentoring, and soon we'll be incorporating a randomized clinical trial embedded into a PDSA cycle using a wrist-worn meal detection device and a patient engagement system from Clue. Next slide. The goal, of course, is to design a type 1 diabetes toolbox of interventions. You can click forward. That starts with population monitoring and the creation of risk predictions and near real-time actionable alerts. Click again. Oh, back one, sorry. And of course, what we want to do is have a menu of potential interventions. So I'm going to have to add one drop and all of our other interventions that are coming on online from both of our previous speakers. And we're going to have to now see whether we can marry these predictions to specific interventions. Next slide. And I just want to acknowledge all the people who've contributed and our funders, the Helmsley Charitable Trust. And I thank you for your time, and we'll take any questions.
Okay, well, I think in some respects I could have had each one of the speakers have their own 1 hour seminar, webinar, because they're just excellent. So I'm going to jump into the questions. First question, it would be, can you automate reinforcement learning instead of asking users to tag? And I guess I'll address this to Amir. Is there a way to put less burden on the patient for putting in all these points and getting involved in their care so intimately?
Yeah, that's a great question. So one of the mechanisms behind it, in addition to picking out instances where the predicted and the actual value were more than 10% apart, another one of them is for the computer, because of the instance where everybody hates manual input, let's put it that way, because users don't put those information and data points in, we can try to estimate, or rather guesstimate, this is a food event, this is a correction with insulin, so on and so forth. But what we found out based on our experience is if we have data to back it up, it makes for much more, a better learning library, as well as much more, the data is way more rich than it would be otherwise if we're predicting. And then another thing that you and I have been going back and forth is, in our case, because the high risk associated with predicting actual values when it comes to type 1, we actually are back and forth with the FDA in terms of what the classification would be. And they want to actually see patient data confirming that, yes, this was a meal event, and yes, I actually corrected. This wasn't the algorithm misfiring, if you will. So that's one of the reasons why we actually try to get users to put those data points in. What we found out is, on average, every day, there are about 3 to 8 tags being generated. And these are instances where we ask the user to actually put information in. And out of those valued, less than 30% of them are completed by the user. And what we found out is, rather than having it accumulate, if they don't put it in 30 hours, they'll just go away and new ones come about. But if we have the user's input confirming what the algorithm figured out, it would just elevate you to a different level as compared to you just estimated. But that's a great question. Thanks for asking.
All right, I'm going to address this to Dan. The question would be, providing some more details on the machine learning algorithms and performance measure. And from my perspective, what about patients who have, many of my type 2s work shifts? I mean, how do you figure in lifestyle? How does the technology adjust to people who have different, work patterns?
Yeah, great. So let's see. So first of all, some of the models are used in the performance metrics. So we use a lot of sort of the standard suite of machine learning models. There's a variety of tree-based models that we use, but we blend that with a couple other things. We have, of course, some I'll call it medical knowledge, just things like how fast carbohydrates get absorbed into the bloodstream, and what's known about the action profile over time of insulin and things like that are also kind of incorporated in the feature design. And then lastly, we also have what's called a compartment model, or a metabolic model, that actually is a simulation of a liver and a bloodstream and a pancreas and so forth, that will actually generate cycles of blood glucose over time depending on different stimuluses. And so those all get woven together into our predictions. And the performance metrics is just measuring the size of the errors retrospectively and trying to minimize those. So that's how that works. And then Jerry, to your question, what happens is every time, let's say you're the OneDrop user, every time you enter new information into OneDrop, it's going to consider that information the next time it makes a forecast for you. So if your phone or your watch is telling us when you're asleep, then we know when you're asleep. And we can actually infer a lot about the structure of your day just by what time you log meals. If you're logging meals 3 times a night and not during the day, then that's a different situation than somebody who's logging meals 3 times a day and not during the night. So the algorithm is watching your inputs very carefully and using that information to adjust its predictions to the time of day that makes sense for you.
Okay, and I want to throw one at Mark. Mark, with the new epidemic of young type 2s, will this affect the work that you're doing with this excellent type 1 model? But you're going to have to deal, as we did in our clinic, with a lot of young, at least teenage type 2s. How does that impact your work?
Yeah, so we started with type 1 population because we are members of the Type 1 Diabetes Exchange Quality Improvement Collaborative. So there was a nice overlap with our efforts there with that larger network. But actually the next phase of this work is going to start to incorporate these predictions on type 2 patients as well. We have a different set of interventions that we're considering and a different clinical team managing those individuals. So we're trying to be thoughtful in all these cases about how to incorporate what we do into clinic workflow. And of course, as I mentioned, we're trying to make sure that we cycle things in relatively rapidly, determine whether there's a signal for improvement or not, move on if there's not, or revise the intervention if there's not a signal for improvement. And as soon as we get a signal for improvement, that's where we pause and we start to expand, verify that signal of improvement, and then think about planning clinical trials.
Okay. Rachel, I don't know what our time, I think our time is up. Is that correct?
Yes. Thanks, Jerry, for keeping us on track. Thank you, everyone, for joining today on today's webinar. Fascinating information. Thank you for the presentations. I think we all learned a lot. We definitely could have had a much, much longer Q&A, but I thank you for everyone for your questions. If you have any more, do feel free to reach out to our presenters directly or reach out to us at DiMe on Slack too. Big thanks to Amir, Dan, and Mark for the excellent presentations, great information, and a special thanks to our Renaissance endocrinologist, Jerry Fisher, for doing a great job with moderating. So just to do some quick roundups, we do have some really exciting presentations coming up next from the Digital Medicine Society here at DiMe. So please join us for our upcoming journal club, which is next week on January 23rd, featuring Ariel Stern and Will Gordon. We'll be discussing their recent article in the New England Journal of Medicine Catalyst titled How AI is Changing Healthcare Delivery. It'll be an Ask Me Anything style event, so come ready for a great discussion. We also have more programming this month, so we'll be piloting a new event called our Lightning Speed Crowdsourcing, a 30-minute event designed to share ideas, seek input, and generate new collaborations in the digital medicine community. We already have 3 presenters lined up for quick pitches, so be sure to sign up to be a part of the action. This one will be very exciting. Join us at dimesociety.org to sign up and learn more about DiMe and digital medicine, and thank you everyone for your time today.